Hi everyone, I'm Harry Wan. I'm a senior majoring in computer science and minoring in math, and this is my engineering honors capstone. It's called Supervised Machine Learning for Pareto Optimization. Before I get into the details of my capstone, I would like to give a big thanks to my advisor, Professor Brian Denton, who's in the IOE department. He was a tremendous help in terms of providing advice and guidance for this project. So before working on my capstone, I was actually working on another project in Professor Denton's lab. And we were exploring Markov decision processes, which are used to model sequential decision-making processes. Essentially, what our MDP is that it's a set of matrices that represent states, actions, as well as rewards in a certain environment. And by solving an MDP, a decision policy can be generated. What a decision policy tells someone is what action to take in what state of an environment to gain the most rewards. Specifically, we were interested in looking at MDPs that take conflicting data sources into account. And to solve these type of problems with these conflicting data sources, we leveraged a branch and bound method. And this essentially involves enumerating through a search space of possible decision policies and pruning the nodes that are deemed to be unoptimal or undesirable given a certain objective function. And it's important to note that different objective functions can be used in this pruning process. So as I was doing this project, I realized that different objective functions yielded different decision policies with different performance measurements. For example, we could have one decision policy that has very high best case performance, but very low worst case performance. And so this would be a more ambitious and a riskier decision in a sense. We could have an alternative policy that has lower best case performance, but higher worst case performance, which would constitute a more risk averse and a more robust decision. So one of the questions I began asking myself was, how does a decision maker evaluate these trade-offs? And how much do they know to weigh different objective functions and performance criteria in a decision-making problem? And so this led me to multi-objective / Pareto optimization. One of the simplest ways to solve these multi-objective optimization problems is to assign each objective function a different weight based on how important a decision maker deems that objective function to be. Now, this seems pretty simple and easy on the surface, but it's actually a very challenging problem because tuning these weights by hand can be very challenging. It can rely heavily on heuristics as well as a large amount of knowledge on a certain domain or a certain application. So I wanted to develop a method that would make this weight tuning process more systematic and data-driven. So the solution is to give a decision maker specific instances of objective value tuples, where each tuple corresponds to a certain past decision. So as you can see here, we have F1 and F2, and this tuple corresponds to a certain decision, where F1 is one performance criteria, and F2 is another performance criteria. So a decision maker will rank these tuples, and the framework will use supervised machine learning to learn weights based on the decision maker's feedback. This is an example of a real-life application in which such a framework would be useful. Suppose you're a financial advisor to multiple clients, and these clients want to know whether to buy or sell stocks at the end of each time point. Now, stocks are volatile and they're very hard to predict, and they can have various worst case and best case prices. One important question that financial investors have to ask themselves is, how much do they weigh the worst case and the best case prices for each stock? And this could be a very challenging question to answer. People might have an intuitive sense of how much they implicitly prefer one performance criteria over another, but it's very hard for them to explicitly quantify this preference. And so the goal for a methodology for this capstone will be to provide a means of specifically quantifying preferences that decision makers have towards one objective function over another. So now I'm going to go over the specifics of the methodology that I developed. So to collect data, I created a simulated decision maker using Python. And each decision maker was initialized with an alpha value that captures how much they prefer one objective function over another. And they are also given a variance level to reflect the way that real human decision makers fluctuate on their preferences from one time point to another. And this is really to make the whole experiment more realistic. The virtual decision maker was tested on a financial data set that was generated using a binomial pricing model. So the name of this framework is called alpha rank. And like I said before, a decision maker is given a subset of the data. They're given n pairs in which they will label from 0 to n for each of the given pairs. A score of 0 represents the fact that a certain pair is the least preferred pair for a decision maker, while a score of n represents the most preferred pair for a certain decision maker. It's important to note that every single pair can only be given an integer score. So essentially, the decision maker is ranking a set of tuples. And from this ranking, the machine learning algorithm will learn a preferred alpha value. And you can see by this diagram that this is an iterative process, and it kind of acts like an optimization cycle. Once we learn or we estimate a certain preferred alpha value, the algorithm will then output another subset of the data that has been ranked based on the learned alpha value. And the decision maker can then go ahead and adjust this ranking to reflect their real preferences. And the framework will once again take that into consideration and adjust what it thinks that the user's preferred alpha value is. In terms of the specific machine learning model used, I decided to use a ranking support vector machine. And what this is that essentially a ranking SVM takes in a list of rankings as its input, and it spits out a decision boundary as its output. And this decision boundary can be used to score future data points. And it does this by solving a quadratic programming optimization problem. And this is a sample of what that optimization problem might look like. Some of the details are rather complicated, so I won't get into that during this presentation. And this is a visualization of a decision hyperplane that will be generated by the machine learning algorithm. In terms of the results of this newly developed framework, some configurations of this framework achieve a relative error of below 1% after 15 iterations in terms of how closely it can estimate a decision maker's alpha value. I found that increasing the number of data points sampled at each iteration also increases performance due to the fact that the machine learning algorithm has more data to work off of. However, one important thing to keep in mind is that with more data points presented to the decision maker at each iteration, the more work that decision maker has to make in terms of making pairwise comparisons between the different data points. And this may make the framework more computationally expensive for the user. Overall, I'm really happy with the results of this Capstone project. And I think I've learned a lot during this process. Thank you for listening. Here are my sources.